Hello everyone. So in the previous video we had seen the gradient descent with momentum. So in this video we will be seeing the RMS prop. Okay, RMS prop. What do you mean by RMS prop? So RMS prop is nothing but root mean square propagation. Okay. So so what is this? So this is an algorithm which can also speed up, okay, the gradient descent. So in the previous video we had seen that gradient descent, okay, with momentum. So in the gradient descent with momentum, okay, what we had seen is that by using the momentum, okay, we are accelerating the gradient descent. Uh, in the same way, the RMS prop, okay, which refers to root mean squared prop, okay, it also, okay, increases the, it also speeds up the gradient descent. Okay, so RMS prop also speeds up the gradient descent. Okay, so consider the diagram over here. Okay, so this is your uh, in the previous example we had seen the contour where we had seen for this contour will ultimately will have to reach to the minimum. So we had seen that, okay, there is a huge oscillation when it takes the vertical path. Okay, so when it takes the vertical path, so it tries to go to the minimum. So this is my minimum. So red color which you see at the center is nothing but the minimum. So I take uh, the horizontal path along with the vertical. So you can see that as and when it approaches near to the red, red color, red dot. So my it it is converted to the vertical, okay, axis. So you can see that when it becomes vertical, so there is an increased momentum. Okay, unlike for the horizontal. So vertical path over here, okay, gives you the quicker progress, um, unlike in the vertical in the sorry, horizontal progress will give you the quicker process, unlike in the vertical progress. So in the previous example we had seen, if you implement the gradient descent, we will see the huge oscillation, which you can see in this also. Okay, how this oscillation takes place in the vertical direction, okay, while making the progress. So let's consider the vertical axis. Okay, it's like somewhat like this. Okay, and this is the horizontal axis, and let's name this as W, or and this as B. So I'm giving some notation for horizontal as W and vertical as B, but in practicality it will be something like W1, W2, okay, and here it will be like W3, W4. So it will be a multiple, okay, parameters which will hyper parameters which is being considered. But for simpler uh, explanation, or for simpler understanding, we are actually taking only two parameters, that is W and B. Here you can see that one, which is W, is nothing but you are going towards the, okay, the horizontal direction. It's nothing but horizontal direction. Okay, and one which is B is nothing but you are going towards the vertical direction. Now here you need to know that one, if you are taking this horizontal direction, okay, that is the double direction, so things will speed up. So there will be increase in speed or increase in the momentum that is taking place. And one, if you're going in the vertical direction, okay, it is actually slowing up the, or you can say reducing the speed. Okay, so speed will slow down. Now for this for calculating, okay, the that is for calculating, so what we'll be considering is, okay, dw and db. So here I am taking dw and db, okay, just like we had seen in the previous video. as the change in the weight and biases. Okay, that is movement of that is moving towards W direction, B direction. Okay, that is in horizontal vertical axis. Okay, so we'll have to compute how much change has taken place in horizontal and how much change has taken place in the vertical direction. Okay, so this dw and db is computed, okay, for in this case, okay, on the current mini batch. Okay, on the current mini batch. So unlike in the previous case where we had seen bdw, now for RMS prop I am taking sdw. So notation, okay, in the RMS prop I am taking sdw for the change in the weights. In the previous case we are taking vdw. In this case I am taking sdw, which is nothing but equal to beta beta times the previous value of, okay, STW. So this is nothing but the previous value of STW plus 1 minus beta, okay, DW square. So for your clarity, this squared operation, what we are doing is the element-wise squaring operations, which we had seen in the previous lectures. Okay, we had seen that what is the square. So we, whenever there is some, when we are taking the different weights W and W2 for that matter, okay, we have to have an equal variances. So for that reason an element wise squaring is being done to bring in the equal, okay, variances between the different weights. This is what I have already taught to you in the lecture, normal lectures. Okay, similarly, okay, we are also calculating the SDB, which is nothing but beta SDB plus 1 minus beta, okay, dB square. Okay, this is nothing but the similarly we are actually squaring the operation, okay, element wise. Okay, now after we compute SDW and SDB, we are actually updating the RMS prop. Okay, RMS prop, okay, updated. That is the parameters are updated, are updated. Okay, so that is nothing but the W is nothing but W minus alpha dw, okay, divided by, okay, so I am taking here in RMS prop I am taking, this is nothing but the previous weight minus the learning rate and the change in the weight that is taking place. For RMS prop, okay, I am taking dw divided by this sdw. Okay, and for b I am calculating as b equal to b minus alpha db, okay, root of s db. Okay, now how these things work. So we have to recall that, okay, in this case when we are taking, okay, w and b, okay, here you can see that w works faster. Okay, that is it is having the faster learning rate. Okay, when it goes to the vertical direction and when it goes to the sorry, when it goes to horizontal direction, it goes at the faster rate, and when it goes to vertical direction it goes at the slower learning rate. Okay, that is the b is nothing but it damps out the oscillation, so your oscillation speeds will reduce. Okay, uh, in with b. Now here you can see that, okay, here your dw value, okay, this dw value, okay, over here, okay, and db value, okay, if we compare this sdw and sdw value is relatively smaller, okay, when compared to this sdb value. So this is relatively, okay, larger. Now when I compute this w is equal to w minus alpha dw sdw root of sdw, so this value will be relatively small. Okay, and when I compute this, okay, b equal to b minus alpha db, divided by root of dw, so it will be relatively larger. So here what it does is the slope is very large in the b direction. So for this b, okay, if you're taking b, so since the root of sdb is the little large, so b will have a larger slope. Okay, so you can see that dw is in this. So when I say db, it is having bigger slope. If you, so that is what you see here. So your b is having the much bigger slope, okay, because it is going at the vertical direction, and it will have larger slope when compared with the, okay, dw. Okay, now, so that is why you see that, okay, when root is db, okay, will have a larger value, okay, over the root of sw. Okay, similarly, okay, I can say that here see that the net effect on this that will have on the updates in the vertical directions are, okay, are divided by much larger number, and it helps to damp out the oscillation. Okay. Whereas the updates in the horizontal directions are divided by a smaller number, and you can see that it is having the much faster, okay, rate of reaching towards the minimum. So net impact of the RMS prop, okay, will somewhat in this way, which you can see that. So this is your um, the gradient descent with momentum. Okay, so in RMS prop we can have a, okay, we'll have a much faster rate. You can see that the you can see that there is a larger learning rate, which you can see here, that alpha is very large, and you can get faster. When alpha is large means you will get a faster learning rate. As a result, okay, you can reach the global minimum quickly. So so in this case, okay, to sum it up, you can say that w is equal to w minus, okay, alpha dw, okay, root of sdw, okay, is your change in the weight, which you have taken um, for the RMS prop. And for b, we have taken b is equal to b minus alpha db root of sdb is what we have taken for the change in the uh, vertical direction. So this is change in the horizontal direction, this is change in the vertical direction. And in RMS prop, you can see that. Okay, let me give the different color for it so that you will identify. So this is what you can see, the RMS prop, which is somewhat, okay, you can see that higher learning rate, as well as it will reach okay, um, the global minimum at the quicker rate, because it is having the higher learning rate. Learning rate is higher when compared to the gradient descent with momentum. So this will have a higher learning rate. Hence, you can say that it will diverge towards the global minimum. Okay. So here in this case, sometimes you see that this SDW as a DB, which you can see here. Okay, there are chances that the value can be also equal to 0. So to avoid that divide by 0, so we'll be putting a small epsilon here. Okay, so this epsilon value is very small, so that it will have a minute value, a minute error rate value is added epsilon, so that this should not face any kind of a divide by 0 thing. So if it is a divide by 0, it becomes an infinity, so it will be computation, it will wrong. So for that reason, we'll be adding this with the smaller epsilon, that is plus epsilon, we'll be adding to this SDW and also to the SDD. Okay, so this is about the RMS prop. So if you have queries, okay, please let me know. Thank you.